Yield enhancement in semiconductor industry. Yield enhancement is a core objective in semiconductor manufacturing, focused on maximizing production efficiency, reducing costs, and improving product quality. Yield refers to the percentage of functioning chips on a wafer, and even small improvements can have a major financial impact. Production optimization plays a key role by fine-tuning processes, minimizing equipment downtime, and ensuring tight process control. These efforts help increase throughput while maintaining high standards. Cost reduction is another major driver. Enhanced yield leads to fewer defective products, reducing waste and lowering manufacturing expenses. At scale, even a 1% yield improvement can significantly boost profitability. Quality improvement is also essential. Higher yields often correlate with better product reliability and customer satisfaction. In summary, yield enhancement aligns production performance with economic goals, helping semiconductor manufacturers stay competitive in a demanding global market. What are semiconductors and yield? Semiconductors are electronic components essential for controlling electrical current flow. They form the foundation of modern electronics and are embedded in nearly every digital device we use: smartphones, computers, cars, and even medical equipment. These devices rely on the precise functionality of chips made from silicon wafers. Producing them involves highly intricate manufacturing processes, including deposition, etching, doping, and packaging. Yield, in this context, refers to the percentage of functional chips obtained from the total produced during manufacturing. A higher yield means more chips are operating as intended, which translates to more profitable production. This is vital for cost control and maintaining competitiveness. For example, if 1,000 chips are produced and 850 are functional, the yield is 85%. The yield formula, working chips divided by total chips multiplied by 100, quantifies efficiency and helps track production quality over time. Why is yield enhancement important? Yield enhancement is vital because it delivers a significant economic, competitive, and industry-wide impact. From an economic standpoint, poor yield performance can lead to staggering losses, up to $68 million annually per fabrication facility. By improving yield, manufacturers can reduce overall manufacturing costs, expand profit margins, and see better returns on investment. Competitively, companies strive to achieve yield rates above 90%, the industry benchmark. Achieving this level provides a faster time to market for new products, ensures stringent quality assurance, and builds trust with customers by delivering reliable and consistent performance. From an industry perspective, yield is the #1 cost driver in wafer processing. Enhancing it strengthens the global supply chain, supports cutting-edge technology advancement, and improves resource efficiency. Together, these benefits highlight why yield enhancement remains a top priority in semiconductor manufacturing today. Why is yield enhancement important? Yield enhancement directly impacts profitability in semiconductor manufacturing. A small increase in yield, just 1%, can result in over $2 million in annual savings per facility. This is because as yield improves, the cost per chip decreases significantly. The graph clearly shows this trend. With yield rising from 70% to 95%, the cost per chip drops from about $14 to under $3. Conversely, products with low yields can drive production costs up by more than 50%, making them economically unsustainable. High-yield processes ensure better resource utilization, reduce waste, and improve overall financial performance. The industry average for yield generally falls between 85% and 95%, and maintaining or exceeding this range is essential for competitive advantage. Every percentage point counts, not only in quality and output, but in financial sustainability and long-term manufacturing success. Key challenges in semiconductor manufacturing. One of the biggest challenges in semiconductor manufacturing is managing defects and contamination, both of which can significantly reduce yield. Defects may include particles, scratches, or misalignment, often occurring at microscopic levels. Even tiny imperfections, such as those smaller than 0.1 micrometers, can compromise the functionality of a circuit, leading to total device failure. These defects can have an exponential impact across wafers, multiplying losses and lowering production efficiency. On the other hand, contamination can be chemical, airborne, or human-induced. To combat this, manufacturers implement strict cleanroom protocols. Cleanroom environments, especially Class 1, are designed to minimize particles and maintain extremely low contamination levels. Air filtration systems and protective procedures are essential for maintaining purity. Without effective control of defects and contamination, the likelihood of low yields and high scrap rates increases dramatically, making these two issues top priorities in process control and quality assurance. Key challenges in semiconductor manufacturing. Semiconductor manufacturing presents two major categories of challenges: process variability and equipment issues. On the process side, maintaining strict control over temperature, pressure, and timing is essential. Even the slightest deviation, such as a change greater than plus or minus 0.1 degrees Celsius, can result in product defects or yield loss. To manage this, manufacturers rely on statistical monitoring to detect variations and implement real-time adjustments that keep conditions within ultra-tight tolerances. Precision is not optional. It's the foundation of successful wafer fabrication. On the equipment side, manufacturers deal with high-cost machinery valued at over $10 million per tool. These machines face ongoing wear and tear, requiring consistent calibration and scheduled maintenance. Unplanned downtime can halt production and severely impact output. To minimize disruption, predictive monitoring systems are used to detect issues before they escalate, ensuring tools remain in optimal working condition and production stays on track. Interconnected challenges. In semiconductor manufacturing, problems rarely occur in isolation. A single issue often triggers a chain reaction, creating what are known as interconnected challenges. For example, a defect detected during inspection can require a detailed root cause analysis. This analysis may reveal that upstream conditions such as temperature drift or material inconsistencies led to the defect. Correcting the problem then requires process adjustments, which must be validated and carefully monitored. Only after these corrective actions can yield recovery begin. This cycle of detection, analysis, adjustment, and recovery not only delays production, but also contributes to substantial yield loss, often in the range of 15% to 30%. For large-scale fabs, that yield loss can translate to over $50 million in annual financial impact. These cascading effects highlight why integrated monitoring, rapid response, and cross-functional collaboration are critical to mitigating losses and ensuring production efficiency. Yield enhancement techniques. Improving yield in semiconductor manufacturing requires a multi-pronged approach using both advanced technologies and proven process control strategies. Process optimization contributes a 5 to 15% yield improvement by focusing on temperature control, pressure management, chemical purity, and precise timing. These factors ensure process conditions are finely tuned to minimize variability and maximize output. Statistical control adds real-time monitoring with tools like control charts, alert systems, data collection, and trend analysis. These help teams quickly detect deviations and act before problems escalate. AI and analytics further enhance this by applying machine learning, pattern recognition, and predictive models to generate smart insights with up to 90% prediction accuracy. Automation increases consistency to 99.9% by reducing human error, ensuring precise repetition, speeding up processing, and improving cleanliness. Defect detection pushes sensitivity to the nanoscale, down to 0.01 microns, using optical inspection, high-resolution imaging, E-beam testing, and early detection systems. Finally, smart maintenance targets 95% uptime through preventive care, health monitoring, precise calibration, and scheduled downtime, keeping equipment performing at its best. Integrated approach. Maximizing yield in semiconductor manufacturing demands more than isolated improvements. It requires an integrated approach. This method combines multiple strategies across process control, monitoring, automation, detection, analysis, and maintenance. When each of these functions is aligned and interconnected, yield improvements become far more impactful and sustainable. The synergy between automation and real-time monitoring ensures issues are identified early, while predictive analytics and AI guide decision-making for optimization and preventive care. Basic techniques alone, such as temperature and pressure adjustments, can result in a 5 to 10% yield improvement. By incorporating advanced AI and machine learning models for prediction and diagnostics, manufacturers can raise that yield gain to 15 to 25%. But the real breakthrough comes with full integration of all tools and methodologies, unlocking a yield improvement potential of 30% or more. These combined efforts not only recover lost yield, but also future-proof the production line through adaptive, intelligent control. Economic impact of yield enhancement. Yield enhancement delivers powerful economic benefits for semiconductor fabs. With optimized yield strategies, facilities can achieve over $50 million in annual savings by reducing waste and improving efficiency. A 300% average return on investment, ROI, is typical within just 18 months, thanks to lower cost per unit and improved throughput. Even more compelling is the 85% cost reduction per defective unit, which directly translates to less rework, scrap, and downtime. The payback period for yield-focused initiatives typically ranges from 12 to 18 months. A cost versus yield curve shows how unit cost drops significantly as yield percentage increases, from nearly $100 per unit at 60% yield to about $30 at 95%. The ROI timeline graph shows exponential returns, reaching 600% by the 36-month mark. To achieve these outcomes, investments focus on 4 key areas: equipment upgrades at 40%, analytics software at 25%, training and development at 20%, and process optimization at 15%. These targeted areas build the infrastructure needed for sustainable, long-term economic impact. Economic impact of yield enhancement. Yield enhancement offers substantial economic advantages across the semiconductor manufacturing landscape. First, it leads to a significant reduction in manufacturing costs, typically in the range of 20 to 30%. This cost reduction is achieved by improving the number of usable chips per wafer and minimizing the impact of defects, resulting in better material utilization and fewer discarded products. Second, companies experience faster time to market. Improvements in yield mean fewer delays in production, enabling products to be launched 3 to 6 months sooner than before. Third, a consistent increase in yield contributes directly to securing a competitive advantage, positioning companies as market leaders. On the investment side, the required capital is $10 million, but the payback period is remarkably short, just 4 months. Annual savings reach $30 million, with a 3-year net present value of $80 million and an outstanding net ROI of 800% over 3 years. Measurement and monitoring systems. Effective measurement and monitoring systems are critical for maintaining high yield, quality, and equipment performance in semiconductor manufacturing. The overall yield is currently at 94.5%, showing a 2.3% improvement. Equipment uptime is 98.2%, up by 0.8%, and the defect rate has dropped to a low 0.05%, improving by 0.02%. With throughput at 847 wafers per hour and 3 active alerts, 2 of them new, real-time awareness is essential. Real-time monitoring systems provide continuous visibility into yield trends, equipment status, temperature at 22.5 degrees Celsius, and pressure at 1.2 millibars. Advanced analytics leverage descriptive, diagnostic, predictive, and prescriptive models. 15 active machine learning models process 2.4 million data points daily, with 95% prediction accuracy and auto-generated alerts. Measurement tools include high-resolution 0.01 micrometer optical inspection, 100% electrical test coverage, real-time SPC analysis, and 24/7 integrated data fusion from multiple sources to ensure continuous improvement and rapid response. Measurement and monitoring systems. An effective measurement and monitoring system relies on a structured architecture and delivers clear operational benefits. The system architecture starts with equipment data sources that provide continuous input. This data is collected in real time and funneled into an AI/ML analytics engine. From there, insights are visualized on intuitive dashboards, enabling fast and informed decision-making. On the benefit side, early problem detection is a key advantage, improving issue response speed by 80%. By catching anomalies sooner, downtime and yield loss are minimized. Process optimization is another benefit, delivering a 15% improvement through refined control strategies and tighter process windows. Finally, the system supports highly accurate, data-driven decision-making with 95% accuracy. By combining real-time monitoring, smart analytics, and clear visualization, these systems ensure manufacturing is not only efficient, but also adaptive and predictive in nature. Future trends and technologies. The semiconductor industry is rapidly evolving, with several transformative trends shaping its future. Artificial intelligence and machine learning are leading the way, driving predictive analytics for proactive decision-making. With an estimated 85% adoption by 2027, AI and ML are expected to enhance fault detection, yield prediction, and process automation. Digital twins are another rising technology, offering virtual modeling of physical systems to simulate, test, and optimize processes in a risk-free environment. Adoption of digital twins is projected to reach 70% by 2026. Quantum computing, though still in early stages, holds promise for solving complex optimization problems, with 25% of research investment anticipated by 2030. Edge computing is also gaining momentum, enabling real-time data processing at the source. With 60% implementation expected, it will reduce latency, enhance responsiveness, and support time-critical applications in fabs and inspection systems. Future trends and technologies. The future of semiconductor manufacturing is being shaped by the adoption of advanced technologies. AI and ML are expected to approach nearly 100% adoption by 2030, followed closely by digital twins at around 90% and quantum computing reaching close to 50%. These technologies are not just trends, they're enablers of intelligent automation. AI/ML applications are already transforming operations. Defect detection using computer vision and machine learning achieves 99.5% accuracy. Predictive maintenance supports equipment health monitoring with 85% effectiveness. Process optimization, though still emerging, accounts for 20% adoption, while anomaly detection through pattern recognition hits 95%. Automated recipe development is also taking hold at 15%. These capabilities contribute to Industry 4.0 goals: higher automation, intelligence, connectivity, and flexibility by 2030. Supporting pillars include smart factories, IoT integration, scalable cloud analytics, and robust cybersecurity, all driving quality, efficiency, and future-ready manufacturing systems. Future trends and technologies. From 2025 to 2027, the semiconductor industry is projected to adopt several breakthrough innovations. Autonomous fabs will become a reality, featuring self-optimizing production lines that dynamically adjust to process conditions, minimizing downtime and boosting efficiency. Real-time AI inspection systems will achieve defect detection accuracies as high as 99.9%, drastically reducing scrap and improving product quality. At the same time, cloud-native YMS, or yield management systems, will be fully integrated into fab operations, enabling seamless data sharing and ecosystem-wide collaboration. Looking ahead to 2028 through 2030, even more advanced technologies will emerge. Quantum optimization will allow for complex yield modeling far beyond current capabilities. Self-healing processes will enable adaptive manufacturing systems that correct themselves in real time. And with global fab networks, Distributed intelligence will empower facilities across the world to share knowledge and coordinate production. These advancements aim to achieve ambitious future targets: 99.9% yield, 50% cost reduction, and zero human intervention in core operations. Key takeaways and summary. The implementation of advanced semiconductor manufacturing technologies delivers measurable, high-impact results. One of the most significant outcomes is yield improvement, where fabs typically achieve a 15% to 30% increase in output efficiency. This directly translates to higher profitability and better resource utilization. In terms of financial performance, each fab can realize an impressive $68 million in annual cost savings. These savings stem from reduced waste, optimized process control, and lower rework rates. Equally important is the speed of issue identification. Advanced analytics and monitoring tools enable an 80% improvement in the speed of detecting production problems, allowing teams to respond more quickly and reduce downtime. Lastly, AI-powered defect detection systems are now achieving 95% accuracy, ensuring that most manufacturing flaws are caught before products leave the line. Together, these outcomes highlight the immense value of intelligent automation and data-driven decision-making. Key takeaways and summary. The key benefits of advanced semiconductor strategies span across multiple dimensions. Increased profitability stems from higher functional chip output, driving financial gains. Quality assurance ensures consistent product reliability, minimizing field failures. A competitive edge is achieved by maintaining a market leadership position, bolstered by innovation and reliability. Resource efficiency focuses on reducing both waste and operational costs. Finally, customer satisfaction rises due to dependable and timely product delivery, reinforcing trust and repeat business. Success relies on 4 critical factors: technology, process, people, and data. Among these, data integration is critical for informed decision-making. Cross-functional teams are essential, combining expertise from engineering, operations, and quality. Continuous learning is an ongoing priority as the industry evolves rapidly. To move forward, the next steps include assessing the current state using baseline yield measurements, identifying opportunities through loss matrix analysis, implementing solutions for systematic improvement, monitoring and optimizing performance, and finally, scaling success through enterprise-wide rollout. The future is now. Yield enhancement is no longer simply about solving individual process problems. It's about transforming the entire manufacturing ecosystem to unlock long-term, sustainable advantages. Today's leading-edge fabs understand that success requires a proactive, integrated approach that elevates performance across all dimensions: process control, data systems, automation, and team collaboration. By investing in smart yield strategies, companies are achieving remarkable returns on investment. Typical ROI ranges from 300% to 500%, a powerful indicator of the financial impact of modern yield initiatives. Even more compelling is the rapid payback period. Most organizations see returns within 6 to 12 months. This short turnaround is enabled by immediate process impact, thanks to real-time insights and streamlined corrective actions. In today's fast-paced, hyper-competitive semiconductor industry, the ability to act now and scale quickly can define your future. The transformation starts immediately, and the opportunity is here.